Hi, welcome to another episode of Miserabile Physics. Today we're going to be discussing electric fields. Now, as we know, most forces can be referred to as contact forces. This is when two objects interact because they're in contact with each other, such as your hands pushing or pulling a cart or a tennis racket hitting a ball. However, the electrical force can act over a distance. That means that there is a force between two charges or two objects even when these objects are not touching. Now, to better understand this, we use the idea of a field. An electric field is like a force field that extends outwards from every charge, right? So there's a charge and it just irradiates like a field of force around it that starts to expand and acts all over space. So that means that at any given distance from this charge, if a second charge is placed there, then that charge will feel a force due to the electric field that is there. So the electric field at point P is considered to interact directly with a charge Q2 to produce the force on Q2. So here we have a charge, and everywhere around the charge it irradiates kind of like energy, like a force, right? So at any point there is a force acting on these lines over here, but no charge will feel a force because no charge is there. However, once we place a charge Q2, say here at point P, if we place a charge here, Q2, then the moment Q2 is there, then that is the moment that this charge feels a force due to the electric field created by large Q. So in principle, we can find out excuse me a second. In principle, we can investigate the field by measuring the force on a small test charge. A test charge is a charge so small that the force it exerts does not interact with anything. It's a charge so small that its effects can be neglected. And one thing to note is that a test charge is always positive. Okay, that's going to be important later on. So, in particular, the electric field at any point in space is defined as the force exerted on a tiny test charge placed at that point divided by the magnitude of the test charge. So what does this mean? This means that the electric field at any point is given by the equation F over Q, where this F, this is the electric force that we learned in a previous video. This force is K Q over R squared. And if we divide this by Q, then another formula for electric field will be equal to K, the charge produced in the field, over R squared, right? So as we can see, the test charge, or the charge that's filling the field, has no effect on the field it feels. All right, so the electric field is solely created by the charge creating it. All right, so let's look at this example here. Calculate the magnitude and direction of the electric field at a point P, which is 30 centimeters to the right of a point charge of -3 times 10 to the -6 coulombs. This is 10 to the -6 coulombs. All right, pause the video here, take a couple of minutes, and see if we can come up with an answer. All right, welcome back. Well, in this example, here we have a charge Q, right, which is -3 microcoulombs. And at 30 centimeters to the right, there's the point P, right? So we have to calculate the magnitude and direction of the electric field, okay? Now, as we know, we're going to put a test charge at point P, right? All test charges are positive. The charge creating the field is negative, so we already know that the direction of the field is going to be in that direction, okay? So let's look at how your textbook solved this example, okay? As we can see, right, the magnitude is kq over r squared, and the direction is towards the charge, right? Because, as we said, there would be a positive test charge here. This charge is negative, opposite charges attract. Okay? Here we go. If the charge would have been positive, then the electric field would have point away from the charge. All right, let's look at this next example. 2-point charges are separated by a distance of 10 centimeters. One has a charge of -25 microcoulombs and the other has a charge of +50 microcoulombs. Determine the direction and magnitude of the electric field at a point P between the two charges that is 2 centimeters from the negative charge. And question B, if an electron is placed at rest at point P and then released, what will be its initial acceleration? All right. Pause the video here, take a couple of minutes, and see if you can answer these two questions. All right, welcome back. Well, let's look at our first question here. We're trying to find the magnitude and direction of the electric field at point P. All right, so here at point P, we're going to place a positive test charge. All right, so this positive test charge is going to feel a field in this direction due to Q1, and it's going to feel a field on this direction as well due to Q2, right? Because if we place a positive test charge here at point P, then it will feel a repulsion from this positive charge and it will feel an attraction from this negative charge, right? So we already know that the direction would be at the left. And the magnitude of this total field will be the sum of the electric field due to charge 1 plus the electric field due to charge 2. Okay. All right, let's look at how your textbook solved it. All right, we have both fields. Okay, they're both having the same direction. So we're adding the fields, okay, as we said, and this would be that. Okay, this would be the magnitude of the electric field, and the direction would be to the left. All right, now let's look at question B. If an electron is placed there, then what will be its acceleration, direction, and magnitude? Well, let's see, right? Now, to find acceleration, I know that the electric field is equal to F over Q, right? Which means that F, which is equal to ma, is also equal to EQ, which means that I know M, I know E, Now I know Q, and I can find acceleration, right? And the direction of the force, well, let's see. So the electric field points to the left, so the electron will feel a force to the right. Since the electric field points to the left, that means that this force also points to the left, okay? Which would be considered kind of like a well, since they will be repulsed by that negative force, right? Here, as we can see, there we go. All right, okay. So let's look at a third example here. This one's a little bit more tricky, as you can see just by the diagram. So here we're trying to calculate the total electric field at point A and at point B due to the charges Q1 and Q2. Now, a lot of this diagram is already solved for us, right, which makes things a little bit simpler. But pause the video here, take a couple of minutes, and see if you can solve this example. All right, welcome back. Well, let's first calculate the field at point A. At point A, we have a field due to Q2, which is positive, right? Q2 is positive 50, which means that it's going to be a repulsion field directly up, right, in the same line of action. And here Q1 is negative 50, so it's going to be a field of attraction along the line of contact, which would be this line right here. So that means that in order to find the total electric field at point A, then I need to break this down into components, right? Find its angle, do Pythagorean theorem, and so on and so forth. Now at point B, Q2 produces a repulsion field in this direction, and Q1 produces a attraction field in this direction. Now luckily for us, at point B, we kind of have an isosceles triangle here, so the magnitudes of the field produced by Q2 and the fields produced by Q1 are the same, which means that this vertical component and this vertical component will cancel each other out, and then we'll only have the two horizontal components right here. All right, let's see how your textbook solved it. Okay, there we go. All right, so first we have the two magnitudes, right? On A, we break down its components, Pythagorean theorem, we have our direction. And then on B, right, we only need to add the horizontal components, okay? There we go, and we have that. All right, okay, hope these examples made sense. Now let's talk about electric field lines. Electric field lines are a way that we can use to visualize the direction and magnitude of an electric field at various points, okay? So electric field lines are drawn so that they indicate the direction of the force due to the given field on a positive test charge. Remember earlier in the video that I said that all test charges were positive? Well, this is why it's important, because this tells us the direction of the field lines. For example, if we have a positive charge creating the field, and I place a positive test charge in these locations, then all these positive test charges are going to feel a force of repulsion, right? Which is why the electric field emanates away from the positive. If I have a negative charge, and I place positive test charge all around here, then all these positive test charge are going to feel a force of attraction, right? Because opposite charges attract. So then the electric field created by a negative charge is a field of attraction. So the field lines point towards the charge. So to represent field lines, right, we can draw the line so the number of lines starting on a positive charge is proportional to the magnitude of the charge. That means the closer together the lines are, the stronger the electric field. The farther apart the lines are, the weaker the electric field. Okay? So field lines can be drawn so that the number of lines crossing unit area perpendicular to E is proportional to the magnitude of the electric field. So as we can see, so if we have something like this and I draw this, this is a weak field, right? The lines are very separated, right? But then if I add a few more, then close to the surface, right about here, the lines are very close together. But if I look at the ends over here, the lines are farther apart from each other. So as we start to move away from the charge, the field starts to become weaker. All right, now in this next few slides, we're going to see a couple of special configurations of charges. The first configuration that we're going to look at is an electric dipole, which is two equal charges of opposite signs. Okay, we have a positive and a negative charge, opposite signs. This creates an electric dipole. Here, the field emanates away from the positive and into the negative. Okay. And these are the field lines, but if I want to find the electric field itself, then the field is always perpendicular to the field line. So this would be the direction of the field here. If I look at this point, the direction of the field will be in this direction, always perpendicular to the electric field lines. In this next configuration, right, we have the field lines of two equal positive charges. And we have something like this. Since they would repel because they're both positive, then you have these lines going kind of away from the lines. What would be different if these two were negative? The drawing will look the same, but the arrows will point inwards instead of outwards. The next configuration that we have is when we have unequal charges, like this. Right? Here we have a +2 Q and a -Q. Notice how, since it's twice the charge, it has twice the number of lines, right? It's 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12 lines. 2, 1, 2, 3, 4, 5, 6. It makes sense. Twice the charge, twice the force, twice the field. And so let's take a look at that. All right, to summarize the properties of field lines. Electric field lines indicate the direction of the electric field. The field points in the direction tangent to the field line at any point. The lines are drawn so that the magnitude of the electric field is proportional to the number of lines crossing the unit area perpendicular to the lines. The closer together the lines, the stronger the field. Electric field lines start on positive charges and end on negative charges, and the number starting or ending is proportional to the magnitude of the charge. This last line start on positive charge, it means that a positive charge, the field starts from the charge and emanates away. And when it says it ends on negative charge, it means that the arrow ends on the charge like this. Okay. Please note that the field lines never cross. Okay. Be very careful when you're drawing or looking at drawing of this. Do not cross field lines. All right, now let's see what happens when we have two charged plates parallel to each other that are charged with equal but opposite charges. Now, as we just saw, field lines will be created, right? Because this is charged, so it's a charged object which creates an electric field. And here we can see the charge emanated from the positive and into the negative, from the positive into the negative, from the positive into the negative. Okay? So notice that the electric field lines between the two plates go directly from one plate to the other, right? As we would expect. Now the field lines between two closed plates are parallel and equally spaced in the central region. Pretty much all this, the field lines are parallel and equally spaced, which means something very important, that in the central region, the electric field and the electric force has the same magnitude at all points. So all here, any charge placed here will feel a constant force from one plate to the next. As long as we stay away from the edges, everywhere in between the plates, a charge will feel a constant force all between the plates, which is very useful to solve this next example. So, an electron is accelerated in the uniform field between two parallel charge plates, as shown. The separation of the plates is 1.5 centimeters. The electron is accelerated from rest near the negative plate and passes through a tiny hole in the positive plate. What is the speed of the electron as it leaves the plate? And show that the gravitational force can be ignored. All right. Pause the video here, take a couple of minutes, and see if you can come up with an answer for this example. All right, welcome back. Well, as we just learned, anywhere in between the parallel charge plates, the force is constant, which means that an electron here is going to feel a constant force, and therefore, is going to feel a constant acceleration. Okay, so if we need to find the velocity, then we need to find the acceleration. To find the acceleration, we need to find the force. To find the force, we need to remember that force is equal to E times Q, right? Electric field times charge. We know this magnitude, we know this magnitude. This is also equal to ma. We know the mass as well, so we are going to be able to solve for acceleration. Then, once we have acceleration, then we can use kinematics, right? Because it's a constant force, so it's everything we learned in our first unit last term. So then we can use that. All right, let's take a look at how your textbook solved this. So here we go. Okay, acceleration is constant because the force is constant. We use kinematics. Okay, Vf squared is equal to Vi squared plus 2AD. Initial velocity is 0, so final velocity would be this. Cool. All right. Now, let's see why gravity has no very negligible effect on this electron. Here we can see that the magnitude of the electric force is this, and the magnitude of the gravitational force is this. That means that the electric force is 10 times 10 to the 14 times greater than its weight. So that difference of force, the weight will not, the gravitational force will not deviate the electron as it moves through the parallel plates. The effects are just way too small. All right, let's look at this next example. Suppose an electron is traveling with an initial speed of VO and it enters a uniform electric field, which is at right angles to VO as shown. Describe its motion by giving the equation of its path while in the electric field. Ignore the effects of gravity. All right, pause the video here, take a couple of minutes and see if you can come up with an answer. All right, welcome back. All right, so what we have here is we have a electron traveling from outside the plates. It gains a certain velocity, and then as soon as it enters the plate, it's in the effects of the electric field and show we have to describe its motion. All right, so as it enters the field, as it enters the space between the parallel plates, it's going to feel the presence of the electric field created between these plates. This electric field goes from the positive to the negative, as we know. So this is going to create an electric field going upwards, but this is an electron, right, which is negatively charged, so it's going to be attracted towards the positive side. So it's going to be attracted downwards. Okay. Now the only force acting on the electron is going to be the electric force, and that electric force is downwards. So horizontally speaking, there is no acceleration or anything like that, right? Only vertically. All right, let's look at our solution. So when the electron enters the electric field, it has a velocity in the x direction, right? The electric field points vertically upwards, imparts a uniform vertical acceleration to the electron of this, right? Okay. The electron vertical position is given by our kinematics formulas, right? BIT plus 1/2 AT squared, okay, which will be equal to this. And horizontally, there is no acceleration because the only force is vertically. So this is x is equal to BOX. Is this starting to look familiar to anybody? Right, 1/2 GT squared maybe, BIT. So since AX is 0, we can eliminate t between these two equations and obtain this. This equation is the equation of a parabola, right? AX squared, which is the same as projectile motion that we learned last term when we were looking at mechanics. Okay? So once again, once the electron enters the plate, the only force it feels is the one created by the electric field. And the force that it feels is going to be in the upward direction, right? But this being a negatively charged is going to feel a downwards attraction. The electron here is going to move towards the positive side, right? Now the force felt by the electron is going to be equal to EQ, right? Which is also going to be equal to MA. So here we can find the vertical acceleration of the electron, right? AY. And we already know that since the only force is vertical, AX is equal to 0. So horizontally speaking, it's moving with constant velocity, which means that x would be equal to VOT. And here, y, right, would be equal to VOT plus 1/2 AT squared. Now, since when it enters the plate, it's moving completely horizontal, there's no initial vertical velocity, so we would have this, okay? Now, from here, okay, we can describe its motion, okay? So here we're describing the vertical motion, here we're describing the horizontal motion. We should be able to combine these two, okay? So we combine these two in such a way that we can say that y is going to be equal to 1/2 a times x over VO, everything squared. And this acceleration right here, this acceleration is equal to, oh, bad color. This acceleration is going to be equal to EQ over m. Okay, there we go. So to write it in terms as the textbook has, we're going to have y is equal to E, the charge of the electron is E, right? Negative, but the acceleration is also negative, so that cancels out. E over 2m x squared over VO squared. And this is the parabolic motion of an electron entering a perpendicular electric field. All right, hopefully these examples make sense, okay? And I want to thank you for watching. I'll see you next time.